All right, so then in chapter 7, what we're going to talk about is this idea of work and energy, right? Before we do that, though, I really briefly need to take a short detour. We need to do some math, right? So we're going to go back, we're going to do some vector math so we can use that to kind of help talk about what exactly do we mean by work and our energy stuff. So we've talked about our vectors before, right? We know how to add them, we know how to subtract them. So let's say I have two vectors, A and B, and I want to multiply them. There's a couple different ways you can do this actually, um, but the way that we're going to do it is something by what we're going to say is we're going to take the dot product of vector A and vector B. So in that case, the way we would do this, we'd write this as this. We have vector A dotted with vector, oops, not vector D. We have vector A dotted with vector B. What we're going to say is that this is equal to the magnitude of A times the magnitude of B times cosine of the angle between them, right? So this is just one way that we can multiply. There is another way, something called a cross product that you can do with multiplying vectors. We're not going to do that at the moment. That'll come later on the semester. For now, we're just going to focus on the dot product. There's another thing. This is just one way that you can actually multiply vectors together, right? So if I have my vectors A and B, I take them, I take A dot B, and what I get is the magnitude of A times the magnitude of B times cosine of theta, where theta is not the angle of A, it's not the angle of B, it's actually the angle between A and B, right, is what we're saying with that. Okay, so yeah, one thing to note right away, right? We have A and B. These are both vectors. However, this end result is actually a scalar. So I take two vectors, I multiply them together, and in this case, I actually get a scalar value, right? I just get a single amount that we're going to have, right? There's no direction associated with this. It's just A times B times cosine theta. So this can be positive or negative. And we can kind of play around with that. We kind of see when is this going to be its maximum value and when is this going to be a minimum value, right? So cosine of theta, right? The cosine of the angle between them. Cosine of theta is anywhere from -1 to 1, right? Those are the possible values that it can have. So it's going to be 1 when theta is 0, right? So when the angle between them is 0. So in other words, we get the maximum value out of our dot product when A and B are pointing in the exact same direction. Then you'll get a larger value for your dot product. If A and B are perpendicular to one another, right? If cosine of theta is 90 degrees, right? So if A were just straight up in this direction, and if B were straight off in this direction, if they were at a right angle relative to one another, then your dot product would be 0. So one way you can kind of think about this is the dot product is kind of measuring, how much are these two vectors pointing in the same direction, right? If they're pointing all entirely in the same direction, the dot product is just A times B. If they're pointing off in different directions, it doesn't matter how big A and B are, the dot product between them is 0, right? Then, of course, if you have A and B pointing in opposite directions, right, you still get a large value here, but it is a negative value, right? This cosine of 180 is what it would be, right? If A is pointing off in this way and B is pointing off in the opposite direction, cosine of 180 would be the angle between them. That would be -1, so you'd have A times B times -1. So this is a dot product, and this is another mathematical tool that we are going to need to use. So let's move on now. Let's go back to our physics. Let's start talking about our work and energy. So we'll start with energy, right? So it's a little bit difficult. We'll kind of put a formal definition to it here soon, but it can be a kind of vague concept at first, right? So you probably already have your own definition, working definition of energy, right? When you talk about energy, if you have a lot of energy, right, you can get more stuff done. You can maybe stay up later, work on your homework more, go out and do a bunch of errands or whatever it happens to be, right? If you don't have any energy, right, you don't want to do a whole lot, right? You don't have a whole lot that you can get done. And it is kind of similar in physics, right? We'll kind of put a more formalized definition to this here in a second. But your own kind of concept of energy is probably pretty close to the formalized version of one, right? You have to spend energy to get things done, right? Is essentially what we're going with. So from a physics standpoint, this is what we're going to say about energy. We're going to say that energy, when you have more energy, right? Energy is the capacity to do work, right? So that's what we're saying. We have energy is the capacity to do work. So of course your next question would then be, well, what is work? I'll get to that here in a second as well. So another couple things about energy that we're going to talk about. Energy can come in different types. You can have different types of energy, as we'll see. We'll play around with a couple different ones, and we're going to see is that you can convert energy from one type to another, right? Of course, a very simple example of this, when you have and you put gas in your car, right, or when you eat food, right, you're taking chemical energy, right, in the form of either your food or your fuel, and then your car converts that chemical energy into kinetic energy, right? It burns the fuel, goes through all this engineering stuff, right, and all the details about what's going on in the engine. Then your car moves forward. But if you don't have any gas in your car, you're not going to get the car to go anywhere, right? So that's kind of one example, right? You're burning that fuel. Your body, again, you eat food, and you then can run around more or something like that, right? You can stay up later, you can go and do more stuff, right? It gives you more energy when you eat more food. So the food, right, or the fuel, whatever it is, contains energy, but that energy can be converted into another type of energy, right? And so that's one way we're going to talk about this energy, right? We can convert it between types, but also another very important thing that we have to keep track of is energy is conserved. What does that mean? So we can convert between different types of energy, but the total amount of energy that we have can't ever change, right? Sorry, the total amount of energy in the universe, I guess is what I should say, right? So for some sort of confined system, the total amount of energy is conserved. You cannot create any energy, you cannot destroy any energy, right? You have to get it from somewhere. So if you want to do something, right, you have to get energy from somewhere, and then of course you've put that energy into whatever it is you're doing. So energy, it's moving around, it's changing forms all the time, but you can't create energy and you can't destroy it, right? So those will be kind of some of the main properties of energy. As we get to new types of energy, I'll kind of explain what's going on. I'll make sure to let you know the different types of energy that we are going to be dealing with. So again, as we said before, energy is the capacity to do work. Well, what is work? Let's get a formal definition of work. So work, we can have a nice strict definition for, and we can say we can define work as F dot D. So we have force dotted with displacement. So we now know what the dot product is. Thank goodness we know that. So we can say this is, again, of course, just F times D times cosine of theta, right? So in other words, whenever you do work on some object, right? So when we're talking about work, I can do work, right? Or I can have work done on me, right? It kind of depends on how you want to phrase it. So that is important to keep track of that terminology. But if I do work on some object, what we're saying is I have to apply a force, right? And then that object has to move in it has to move in such a way that there is some sort of component between of the force and the displacement that is in the same direction, right? So if I push on something and it moves in the same direction that I push it, right, depending on how hard I'm pushing on it and how far it goes, right, and then of course the angle involved in these, I will have done some sort of work on that object, right? So of course, what do we mean by this? We can talk about some simple examples, right, and just kind of talk conceptually about it. We're not going to put any numbers to things right now. We're still just kind of trying to build up our intuition of what this work and what this energy stuff is. One thing we can say right now, though, is this is the units of this would be in Newton meters, right? Newton meters, right? This is a newtons times meters, and 1 Newton meter is 1 joule. So 1 joule of energy, right? So if you have 1 Newton meter of work, right, that you do, you've basically put 1 joule of energy, right? So work has units of joules, and joules are units of energy, right? So work is, again, kind of, you can also think of it as a transfer of energy. When you do work on something, you're transferring energy from yourself to this other object, right? So let's look at some simple, just kind of conceptual examples that we can talk about with this work stuff. So let's say I have a briefcase, right? And it is sitting on the floor. So this is our first thing. So what are the forces acting on this briefcase? Of course, we have the normal force and gravity, but for now, we're going to ignore the normal force. We're going to say that we have this. Well, I'll tell you why we're ignoring it here in a second. We have gravity pulling it down, obviously. And what we're going to look at is what is the work being done on this briefcase if I pick this briefcase up, right? So there's no more normal force on it, right? I've lifted it off the ground. You can kind of see I've drawn it slightly off the ground. I'm in the middle of lifting it up, and I apply a force F on this briefcase. It goes up, and so the displacement is also up. how much work did I do and how much work did gravity do, and then of course what was the overall work done on this briefcase. So in this case, if we have this briefcase, I pull it up, I apply a force up, it goes up, the work from me, right, the work that I did, would just be F times D, right? I'm pulling it up, it's moving up, and so I am doing work. The work from gravity, however, would in this case be negative mg, right, the force of gravity times D, right? So if I pull this briefcase up, I am doing positive work, and gravity is doing negative work. Don't worry too much about the numbers. We'll get into some more details about this. We'll do some more examples for now. But for now, I'm just trying to build up your intuition of, when is work being done and kind of what is going on with this stuff. So this is one example. Let's look at a slightly less intuitive example. Let's say I have picked this briefcase up, right? We did some work. It's now in the air. I am now carrying it, right? And then I carry this briefcase across the room, right? I walk across the room with it. The force that I am applying on it is up, right? I just have to hold this briefcase still. I'm just holding it up. Gravity is pulling it down, but the displacement is to the right now. I am taking this briefcase and I'm moving it at a constant velocity, and I'm walking across this room. During this time, what is the work that I'm doing? Well, the force I'm applying is up. The briefcase is moving to the right. So actually, in this case, the work that I am doing on this briefcase is 0. This might seem a little weird at first. It'll start to make more sense when we kind of start to, as we keep going with this stuff. But for now, again, we're just saying, right, our work is our force dotted with our displacement. If I have F dot D, right, these are at a right angle relative to one another, I'm pulling it up, right? The force I'm applying is up so it doesn't fall down, but I'm carrying it to the right here. It's moving at a constant velocity, so the net force on it is 0. These will be my only forces. You have a force up and a force down. The net force is 0. During this time, I am not doing any work on this briefcase, right? How much work is gravity doing during this time? Also 0, right? So yeah, so in this case, again, it might seem a little bit weird, but if you carry this briefcase across the room, you will actually not have done any work on it, right? Assuming you're carrying it at a constant speed. Of course, when you get into throwing it or speeding it up or anything like that, then we'll see how that kind of changes things. But carrying this briefcase across the room at a constant velocity, no work is being done, right? Then, of course, we can say, okay, now I'm going to set this briefcase down, right? So we'll say my force is still up, right? I'm setting it down, but I'm still actually exerting a force up. Gravity is pulling it down, and now the displacement is down. In this case, now I am doing negative work, right? I am pulling it up still. I'm setting it down, but the force I'm applying is actually still in the up direction, right? Because I'm not letting it fall just freely. I'm not pushing it down or throwing it down either. I'm just not applying as strong of a force as I used to be. So the forces that I'm applying is up. The displacement is down, so I must be doing negative work. They're in opposite directions. And then the work of gravity, sorry, this is the work from me, this is the work of gravity, must be positive m times g times c. Right now, gravity is pulling it in the same direction that it is moving, and so gravity is actually doing positive work on it, right? So we can talk about one more situation here, right? So in this situation, right, we said, so here obviously I'm doing positive work, here I'm doing negative work, right? And gravity is doing the opposite as I'm pulling it up or setting it down. For this in-between case, we were moving it horizontally, and we said no work was being done. How can I move it horizontally with some work being done? What's an example I can think of for that? Well, very simply, let's take this briefcase. Let's set it on the floor now, right? And let's push it along the floor. Now, what are all my forces acting on this briefcase? And let's just kind of see which ones will be doing work and which ones will not. So as I push it across the floor, gravity is pulling it down. The normal force is now pushing it up, right? I am pushing it in this direction, right? I'm applying a force to it to the right as I push it across this room, but friction is trying to pull it back in the other direction. Which way is the displacement though? I am actually pushing it forward, so the displacement is to the right. So my four forces, right? I'm pushing on it. The normal force is pushing it up. I'm pushing it to the right. Gravity's pushing it, pulling it down, and friction is pulling it back. So which of these forces are doing work? Obviously, if my displacement is to the right, as we've seen before, the normal force and gravity are not doing any work in this case. However, I am doing work. Now I am doing positive work again, right? I am pushing this across the room, right? It is moving across the room. I'm applying a force. It's moving in the same direction. So you would just have F times D. The work from friction, however, be negative F times D. Friction is actually trying to pull it in the opposite direction. It's not succeeding, but it's trying to, right? It's still applying a force. The friction is pulling to the left. The displacement is to the right. And so in this case, friction is doing negative work, right? So essentially, right, we have these couple different situations here. Again, our overall definition of work for some individual force is F times D times cosine of theta. So the directionality is important, even though work itself, right, this is a scalar, so work is a scalar. We're just talking about the amounts of work being done, but kind of figuring out what direction these forces and these displacements are at does still play a role in whether or not work is being done. So let's look at this in a little bit more detail now. Let's try and figure out a better formula for this work, right? So we know how we can calculate the work from some sort of forces. However, what if there's something that's just moving around? Can I figure out how much work is being done on it or how much work has been done on it or anything like that? Let's look at how this work is then going to actually affect the motion. Let's take this formula is what we're going to do, and we're going to tie this back to our Newton's laws and our kinematics. So here's how we're going to do that. We know that forces apply work. Let's look at what the net work being done on some object must be. Well, if the net work being done is based upon, right here in this case, we had all different kinds of forces. Some of them were doing work, some of them were not. The net work then must be related to the net force, right, times the displacement. And for this case, we're going to say our net force and our displacement are in the same direction, right? Just to keep things simple for us for this derivation. But here we have this. We're going to say that the net work on some object is equal to the net force on that object times the displacement. So how else can we rewrite this? What do we know that the net work is equal to, right? F net must be equal to ma. So this allows us to write the net work is equal to m times a times d. So this is also another correct way to write the net work being done, right? The mass times acceleration times the displacement. But let's talk about it. Let's kind of tie this back to our kinematics and see what else we can learn. If we remember from our kinematics, we had this formula here. V final squared equals V initial squared plus 2a times d. So here's an a times a d. Here's an a times a d. Let's solve for this and plug it into there and see how we can rearrange our network. So we can very simply see, just divide by 2, subtract this over, and what we get is this. We have v final squared minus v initial squared divided by 2 is equal to the acceleration times the displacement. So let's plug that in. The network is now equal to m times v final squared minus v initial squared divided by 2. Or we can rewrite this a little bit more organized. We can say the network done is equal to 1/2 m v final squared minus 1/2 m v initial squared. So what does this look like now? This looks like some sort of change in this value, right? We have a final minus initial, right? We have 1/2 mv final squared minus 1/2 mv initial squared. So what is 1/2 mv squared? What is that? This is a value, right? We're saying that the network is equal to the change in whatever this value is. This value is something that we're actually going to call the kinetic energy. So the kinetic energy, this actually is in units. This, of course, right, if we follow our algebra through, this has to be in units of joules. This is an energy, right? And this is actually the energy of some object associated with its motion, the kinetic energy of that object. And what we're saying is the net work done on some object is equal to its change in kinetic energy. So if the kinetic energy of an object changes, we know that there must have been some sort of net work done on that object. So again, as we said before, this is our energy associated with motion. So again, if we go back to the briefcase, we can kind of think about it this way. If I apply a force on this briefcase, right, and I accelerate it, right, it started with some velocity, it ended with a different velocity, there must have been net work being done on that briefcase. But if we think back to our examples that we were saying earlier, right, let's kind of combine all this stuff now. If I'm pulling this briefcase up at a constant velocity, right, if its velocity does not change, what's the net work being done? If there's no change in velocity, if this final and this initial are the same, then the net work being done must be 0, right? So we can see this though pretty clearly, right? If I'm pulling this up at a constant velocity, it means that I am doing positive work and gravity is doing negative work such that the overall net work done on the briefcase is 0. Again, while this briefcase is being carried horizontally, in this case, right, it's not accelerating, it's not speeding up, it's not slowing down. In this case, our forces, again, are perpendicular to the motion as well. And so there will also be no work being done, right? And again, in this case, if I set this down at a constant velocity, then of course we have I'm moving it down, right? Sorry, I have my force pulling up though, it's going down. Gravity's doing positive work. I am doing negative work. And similarly with our friction example, right? If I'm pushing it along the floor at a constant velocity, right? Then no net work is being done. But that's because I am doing positive work and friction is doing negative work, right? If it were just up to me, this briefcase would be speeding up. If it were just up to friction, this briefcase would be slowing down, right? So this is kind of how we can kind of tie all this stuff together. The network um, done on some object has to be equal to the change in kinetic energy. So whenever we see some object accelerate, then we know that there's some work being done. So this is actually another problem-solving tool that we're going to have that we'll use and that we'll kind of see some more examples with. We'll also get into more different types of energy, but for now, again, you can think of this. We have our kinetic energy, right? So is 1/2 mv squared. So just if something is already moving, if it has some sort of motion, um, there's energy associated with that motion, and the amount of energy is 1/2 m times v squared. So it's dependent upon how much that object weighs, what the mass of the object is, but also it's dependent upon the speed squared, right? So yeah, so with this, again, this allows us to look at, we can now look at a system, we can look at all the forces, we can tell how much work is going to be done, and we can very quickly figure out how fast it's going to be moving, or we can go backwards, right? We can look at how fast it's moving and look at how its velocity is changing or how its kinetic energy is changing, something like that. We can figure out what the work being done is. We can go back and we can figure out what the forces are, right? So this is what we'll do for this section. As we go throughout this chapter, we'll kind of encounter a couple more types of energy, and we'll kind of see how we can kind of move this energy around between them, right? So that's what this chapter is going to be all about, is following this energy as we do work.